Welcome to section 9.1. We're going to be discussing sequences. A sequence is an ordered list of real numbers which can be expressed by a function whose domain is a set of natural numbers. Note that the graph of a sequence will be displayed in points n comma a sub n, which kind of replaces the x comma f of x or x comma y coordinate. They are not connected since the domain is a set of natural numbers, not real numbers. There's three ways to represent the notation. There's function notation, where you have your braces, which builds your sets, and then we list out all of our values based off of where we start with our n value to where we go to infinity. Then there are times when they don't even supply that because it's just generalized in the definition to start at 1 and go to infinity. Or you can start at any other location. If you're going to start somewhere else, you have to identify it. Same thing with ending somewhere. You have to change infinity to wherever you want to have a finite sequence. Formula for a sub n, this is the most popular one to use. It's assigning this inside sequence function to an actual function name, kind of like having f of x is equal to x over x plus 1. And then the ordered list of terms where they'll give you usually 3 or 4 terms within your ellipse dots and then give you the function notation after that. So if we were asked to list 5 terms of the sequence of a sub n equals 3 to the n over 1 plus 2 to the n. We substitute in the 1 in for n, so that's 3 to the first over 1 plus 2 to the first. So 3 over 3 is 1. Now, as you're going along here, you might start to just recognize the pattern or just put in all the values right away. 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th, and do the same thing to your denominator. 1 plus 2 squared, 1 plus 2 cubed, 1 plus 2 to the 4th, 1 plus 2 to the 5th. And then crunch the numbers. We'd have 9 over 5, 27 over 9, which reduces to a 3, 81 over 17, and let's see, 243 over 33, which reduces to 81 over 11. You may also be asked, here's some terms of a sequence. Write the function for the sequence. So if this pattern continues, which the dots say they do, what I would do is label n equals 1, 2, 3, 4, 5 right above it, since that's your first term, second, third, fourth, and fifth based on those n values. What we would do next is say, okay, look for a pattern in the numbers. Well, I noticed that we have alternating signs. So that's going to be -1, and since the first term is negative, raise it to the n power. Now, if that first term was positive and the second was negative, then we would put n minus 1. So 1 minus 1 is 0, and of course -1 to the power 0 gives us 1. Looking at my numerators, I notice that there's base 2 numbers here. 2 to the first, 2 squared, 2 cubed, 2 to the 4th. Since this pattern is continuing, then back here to the left of 2 to the first, above -3, would be 2 to the 0 power. So looking at your n values and comparing them to the power, it looks like we're always subtracting 1 from the n, and that establishes our exponent. So that will be in the numerator, so it'll be -1 to the nth power times 2 to the n minus 1 power. In the denominator, we have the same thing with the 3's. I see base 3 numbers. So below the 2, I'll put 3 to the 0, and below the -3, I'll put 3 to the -1. So in my denominator, now going from 1 to -1, 2 to 0, 3 to 1, I have to subtract 2 from my n. And there's my function. Now, sometimes we have to clean this up to the point where we like to have everything with the same exponent. So on the bottom, n minus 2, if I multiply my fraction by 3 over 3, that 3 to the first times 3 to the n minus 2 will add 1 to this exponent, and that will create an n minus 1. And then I'm going to do the same thing to my n. To make it an n minus 1, I'm going to take a negative away from the base, multiply it to this 3 in the numerator, and that will give this negative 1 an n minus 1 exponent. So now I can rewrite this as negative 3, and I can have the negative 1, the 2, and the 3, all same bases, put them all together to one exponent, a negative 2/3 to the n minus 1 power. If we were asked to plot terms on the graph, well, we'll kind of do the same thing. Pick your n equals 1, 2, 3, 4, 5. Treat that like your x column. A sub n, we'll start plugging in the numbers. 2 to the first over 1 plus 3 is 4. 2 to the fourth equals 1/2. That's our point, 1 comma 1/2. We'll plot it. Then we'll have 4 over 5. That will be 2 comma 4 over 5. Plot it. Then we'll plot 3. When n is 3, that's going to give us 6 over 6, which is 1. So 3, 1 we plot. 8 over 7, 4 comma 8 sevenths. Then we'll have 10 over 8, which reduces to 5/4. We'll plot that point. But those are my points, and they're not connected. So when we're looking at this graph here, it appears that we're starting to increase, but it looks like we're apparently starting to slow down. And we could choose other numbers. For example, we could go out to 10. That'd be 20 over 13. And if we plotted 20 over 13, we would be somewhere around this halfway point here between 1 and 2. So again, things are starting to slow down. So when a sequence terms approaching a limiting value, that means as my fraction begins, as my dots begin to flatten out, the sequence is said to converge. So if you remember back in Calc 1, we talked about limits. The limit as n approaches infinity of a sub n, it's equal to some limit value. So the definition of a limit of a sequence is very similar to the definition of a limit of a function. In fact, it's almost identical. What's missing is the fact that these points are not connected by a curve. So the limit as n approaches infinity for a sequence function, it's equal to L, or it can be written this way as well. If we can make the terms a sub n as close to our capital L limit as we like by taking n sufficiently large, oops, come back here. If it exists, if our limit exists, then it converges. If it doesn't exist, then it diverges, or we call it divergent. Both these examples are sequence graphs where we plotted the points, and they are approaching a limit as we go out to infinity. A more precise version of definition 1 is as follows. You have your same beginning here, your limit as n approaches infinity of a sub n equals capital L. If for every epsilon greater than 0 there is a corresponding integer capital N, such that if n, that's the number we're working with here, is greater than capital N, then the absolute value of a sub n minus the limit is going to be less than epsilon. So basically it means that for n is greater than capital N and epsilon is greater than 0, the terms of the sequence that converges to our limit L will lie within the band between y equals L, our limit plus epsilon, and our limit minus epsilon. And that is represented by those two green lines here. So the precise definition of a limit at infinity, when we use a function notation, is the exact same setup for sequences. So one thing that we can do is we can create another theorem that states the following: that since we're used to using functions f of x for all real numbers, if the limit as x approaches infinity of f of x equals a capital L limit, and f of n is equal to a sub n, where n is an integer, then the limit as n approaches infinity of a sub n is equal to L as well. So we can use and change our sequence function back into regular function notation and evaluate our limits the same way. For example, we might need to have it as a function, so we can use L'Hopital's rule or things of that nature. So consider the function f of x equals 1 over x to the r power, and the sequence a sub n equals 1 over n to the r power, where r is greater than 0. So graphing my function is this blue curve. Plotting points starting at 1 is just hitting those natural numbers. So since f of n is equal to a sub n, in other words, you take the n values that for the sequence function, plug it into the f of x function, they're landing on the curve. Therefore, the limit as x approaches infinity of 1 over x to the r is equal to 0, then so must that be true for our sequence function. So if we had to find the limit of the sequence as we looked when we were graphing it, that a sub n equals 2n over n plus 3, if it does exist, convert it into function notation f of x. So we'll take the limit as x approaches infinity of 2x over x plus 3. By using L'Hopital's rule, you take the derivative of the top and the derivative of the bottom, because as it stands, going to infinity for both x's gives me an indeterminate form, infinity over infinity. So that tells us to use L'Hopital's rule. You taking the derivative, you get 2 over 1. Therefore, now the limit as x approaches infinity of a constant value 2 is 2. And therefore, it converges. So if our function converges to 2, so must our sequence converges to 2 as well. All right, don't forget some of your basic limits properties with functions will also hold true for your sequence functions. If I'm adding two sequence functions, you can separate them as two individual limits. Same with subtraction. Multiplication, you can factor out the constant, that scalar factor. Limits of constants are always constants. Multiplying two limits functions together, you can multiply the limits together. Same thing with division, except make sure that the denominator does not have a limit that's approaching 0. And if your sequence function is raised to a power, you can find the limit first and then raise the limit value to a power. Again, the power has to be greater than 0, and your sequence function has to be a positive function, which means all its terms must be positive. You can't have any alternating signs there, or a series of negative terms. So find the limit if it exists for a sub n is equal to 3n over n plus 1 minus 1 over 2 to the n. So again, I'm going to use my function notation. And let's see, because I'm subtracting, I will separate the two limits. And now I'll evaluate each one separately. So here you can see, very similar to what we did earlier, take the L'Hopital's rule of the top will be 3, L'Hopital's rule of the bottom, take the derivative will be a 1. That will be a limit of 3. And here, the bottom is constantly getting bigger while the top stays 1, so this approaches 0. So our limit value is 3. Therefore, by that theorem, our sequence function must also approach the same value of 3. Find the limit, if it exists, of a sub n equals the natural log of n squared over n. So again, turning it into a function f of x, again, you can see this is an indeterminate form, infinity on the top, infinity on the bottom. So we'll take the L'Hopital's rule, take the derivative of the top and the derivative of the bottom. So we have a chain rule on top. It's going to be 2 times our function, natural log of x, and then the derivative of the inside, ln of x, is 1 over x. Derivative of x is 1. So to simplify this, multiplication of 1 over x would definitely put the x back into the denominator. So we'll also factor the 2 to the front of the limit, and we have another indeterminate form as x goes to infinity. So we'll take the derivative, top and the bottom again, using L'Hopital's rule. We'll get 1 over x on the top, we'll get 1 on the bottom. So now we can find our limit. The 1 on the bottom is not needed. As x approaches as x approaches infinity, you're going to get a 0 here. So this is 2 times 0, or 0. And therefore your sequence function is also approaching 0. All right, our next definition of the limit as n approaches infinity for a sub n is equal to infinity means that for every positive number, capital M, there is an integer, capital N, such that if n is greater than capital N, then a sub n is greater than capital M. Find the limit if it exists. All right, so here, changing it back into function notation. Again, we have another indeterminate form of infinity over infinity as we plug in the x's. We take the derivative. So now the derivative of the bottom is 2. The derivative of 2x is 2x times the natural log of 2. Now the top is constantly going to get bigger, so therefore my limit does not exist, and therefore either for my sequence function, it diverges as well. So we're just constantly getting bigger and bigger, so therefore we're diverging.